So, in the previous lecture, we have seen what electron energy loss spectroscopy is, how inelastic scattering is, and what kind of signals you can get. Let us now see how do you achieve this in the TEM. I have just given you a broad mention of the post column spectrometer, and also I used terms like dispersion plane and so on. Let us just understand conceptually how this works, and let us see some examples with some specific case studies. So, this is a figure that I showed you earlier again. So, if I have the image plane, if I look at the vertical axis and imagine that along the so if I look at the vertical plane and I see that there is an energy axis along the vertical plane beyond the image plane. Along this direction, as a function of energy, if I think that the energy variation is described, what I need to understand here is, if I now compare it with the electron microscope and the layout of the microscope, the important concept here is the inelastically scattered electrons that have undergone certain loss of energy, a certain measurable loss of energy, say ranging from 0 to 3000 eV for example. Let me compare two cases. Let us say I am looking at electrons that have undergone energy loss of 20 eV and electrons that have undergone a loss of 50 eV. Along the electron microscope, when along the electron microscope axis, when they are passing through the objective lens and the illumination system, what we know is, in comparison with the 200 or 300 kV electrons which are converging at a certain point, I am not considering the lens aberrations yet. The electrons which have lost some energy, so 200 minus 200 kilo electron volt minus 50, so which is 199450 or 199480, these two would not converge at the same point. And now, when I know that the velocities of these electrons are different and they would not converge at the same location, I can use this to now turn this trajectory of the electron beam by introducing a sort of a strong magnetic field by turning it through an angle of 90 degrees. And based on the energies and the change in the velocities or the convergent points, if I introduce a concept called as a magnetic prism, I can see that along the energy axis, the electrons which converge at 200 or 300 kV have not lost any energy, or let us say forming the zero loss peak. Based on the variations in the angles of convergence and the velocity differences, I can start dispersing them at different energies. So, this plane where I am now converging these electrons of different energies or separating these electrons of different energies is called as a dispersion plane, and I want to stay away from the influence of the strong magnetic field that is already existing. So, I deviate the path slightly away from the optic axis of the microscope. So, the design of the post column or the omega filter is such that if I look at the omega filter, I have two deviations which happens at an angle of 90 degrees. It goes through a filter where I have my dispersion plane here, and I recombine them back along the column of the microscope. So, the shape of this looks like this omega symbol, and that is why I call it as an omega filter. So, the whole physics concept I am relying on here is, if I have a magnetic prism and a combination of electrostatic lenses again, I can disperse based on the energy here that the electrons are not going to coincide at the same point. I can get an energy dispersion plane, and this is what your spectrum looks like. If I am now doing this within the microscope column, I call it as an omega filter, and if I do it with some kind of a post column filter, I call it as a post column energy filtering system. Either I have the GIF filter or I have the Cepheid filter, it is the Seos electron filtering system or the Gatan imaging filter system. So, the construction is based on similar principle. There is something called as a drift tube, where the electron that has undergone forward scatter has a combination of the zero loss electrons and the low loss and the core loss electrons. And here I have a sort of a magnetic field free drift tube, which is now deviating my path of the electrons to turn through 90 degrees. And here, through a series of imaging optics and whatever concept of magnetic prism and dispersion that I told you on, I can display the energy axis. And in the old days, you had the photodiodes, and now you are having the CCD camera. Each pixel corresponds to a specific energy, and you are seeing how my spectrum is collected relative to the energy here. If I am collecting the spectrum such that every pixel corresponds to certain energy value, this is spectrum. And instead, if I use a window and I display the image that is collected within a specific window, I get the energy filtered TEM image. So, this is how I can actually get either the spectroscopic information or the image information. And typically, the spectral resolutions combined with STEM are much better spatial resolution as well as the energy resolution as well than the FTEM images that I record. So, this is how the concept of how you are achieving energy filtering in an electron microscope column or beyond the electron microscope column. So, either with an omega filter where I use two prisms to go back and join this path of the electron microscope column again. So, typically this is positioned between the objective lens and the intermediate lenses. Geol has this. So, this comes from the microscope manufacturer only. You cannot retrofit an omega filter. In fact, there are some groups who have developed these, of course, and they would have done a retro modification of the whole thing, but most commonly for common users, you cannot retrofit an omega filter. The post column filter, you can retrofit it on an existing microscope, and each method has its own advantages and disadvantages. If I think of what are the main advantages of an omega filter, if I am primarily interested in separating the elastic and inelastic scattered electrons, and I am not focusing a lot on the energy resolution only, I can actually get very good high contrast images even for beam sensitive and kind of very low atomic number elements that I am using for improving the contrast, such as biological samples or polymers. And also when I want to do multiple imaging that I do with various combinations in conventional imaging, your electron beam is always passing through an omega filter, and you have an inherent filtering channel which you can combine with the other collection that you do. For example, the diffraction patterns or the convergent beam electron diffraction patterns or whatever imaging or diffraction information I record with a conventional TEM, I can also have an energy filtered information also recorded. So, this kind of maximizes the information you get, but there is a compromise on the spatial and the energy resolution that you get. If you have an omega filtered system combined with a monochromated source, you can certainly achieve a very high energy resolution as well. But modern day microscopes also have an in column chromatic aberration corrector with a post column energy filter, which gives you the best energy resolution, which also has a monochromator as well. So, when you want to achieve high energy resolution, the construction would be slightly different from an omega filter kind of a construction. I am not saying that it is not possible to do this, but there are some limitations on this. With the post column energy filter, you can retrofit it onto the system. If you have a monochromated system, you can certainly achieve very good energy resolutions by exciting the monochromator. Typically less than 100 milli electron volts you can certainly achieve. You can get as low as 10 or 20 milli electron volts as well. But most commonly, if you are looking at either a Schottky FEG or with a thermionic emitter or with a cold field emitter, the energy resolutions on the post column filters are anywhere between 1 eV for a Schottky FEG or beyond 1.5 eV for a thermionic emitter versus around 400 milli electron volt or 0.4 or 0.3 EV for a cold field emitter. These Schottky FEG in combination with a monochromator can help you achieve anywhere between 10 to 30 milli electron volt resolution as well. So, there are several improvements that are happening on improving with the energy resolution. There are two things here, one is energy resolution and the other is spatial resolution. This is the typical ranges of energy resolution you can achieve. I was talking about 1.5 EV for a thermionic source. Typically, if you have a lanthanum hexaboride filament, you can achieve that, but with a tungsten filament, you are somewhere around 3 EV. With a monochromator and a Wien filter, you can get as low as 0.1 EV. The neon microscope and also the modern day dedicated spectrometer microscopes are now achieving 10 to 20 milli electron volt resolution as well. So, which is 0.02 EV resolution, which is extremely good, and this is very useful for looking at specific analytical information from specimens as well. So, when I look at typically the kind of data I get from low loss or no loss spectra, around the zero loss peak, I typically have the elastic and the forward scattered electrons, and within the low loss region, I am defining it as arbitrarily the electrons that have undergone an energy loss of around 50 EV. When I am looking at the scattering phenomenon, I have either the single or elastic scattered events and inelastic scattered events. This is what you get with the electron energy loss spectra, but most single, plural or multiple scattered events are typically what you record in the EELS spectra, and you can start modeling them. There is actually a software called as EELS model, which is developed by the EMAT group. It is very useful to simulate the EELS spectra you get. This is very useful in understanding the effects of specimen thickness and other associated drift or variations you get in electron energy loss spectra that you record. Most specimens which are very thin and with uniform thickness typically around 20 to 30 nanometers or lower, you get nearly single or plural scattering events, and with this you get very good quality EELS data. So, if I am looking at the scattering angles for EELS, we talked about the convergence angle and the collection angle. If I say E0 is the beam energy, typically 200 or 300 EV, and if E is the energy loss that has happened, if I am ignoring the relativistic effects for now, I can typically define the scattered angle of the inelastic scattering event proportionate to somewhat as E over 2 times E0. So, for example, a 50 EV over when I consider a 300 kV, this is my scattering angle in radians, and you can understand when I look at how the scattering angle is related to the energy loss. When I am ignoring the relativistic effects, it is approximately with this kind of an angle. A more precise approximation can be given with this kind of an expression based on the velocity of the electrons and how you can get the more precise angle, and this gamma here is given by this kind of an expression. This gives you a fair enough ballpark figure. So, if I look at the cutoff angle or the acceptance angle for my entrance aperture, I can have it as somewhat like this. So, typically if I am recording information from 0 to 3000 EV, I can look at the scattering angle as somewhat between 3000 over 600,000 if it is 300 kV TEM or 400,000. This would range anywhere between 5 to 10 milliradians, and you can typically achieve this with a 2 millimeter entrance aperture. So, that is what you have when you are physically defining the entrance apertures and so on for your EELS spectrometers. All the energies are in kilo electron volts like I was mentioning, and the angles are in radians. And if I look at how the data looks like, the low loss data or the zero loss peak data, if I look at the zero loss peak, actually if I zoom into that zero loss peak that I showed you earlier, there is a small shift here. I have to compensate for how much this is, and in an ideal scenario, you should have a single line corresponding to this value 0 here, where all the electrons that have not undergone any kind of energy loss should be concentrated only here. But if you look at the practical effects, there is always a tail associated with the zero loss peak. The zero loss peak is having definitely no loss in energy. The exposure times, the recording angles, and the way you get the data, whether I am in diffraction mode or in image mode, if the exposure times are not calibrated properly and done carefully, you can actually damage the spectrometer. So, I would suggest you always shadow somebody who is more experienced in this, and please pay attention to the details on which exposure times are used for which energy ranges and what is the maximum intensity you are using for zero loss peaks and convergence angles and collection angles. For every instrument, there is enough experience that is there and specific factory calibration settings that are given to you. Please follow them to be sure that you do not damage a spectrometer. These can range anywhere from $500,000 to 2 million euros, and it is extremely expensive, especially the post column EELS spectrometers. So, be very careful. When look at the zero loss images, for example, here is something which I have from a no loss or a sort of forward scattered electrons that are collected, a bright field image, but here is a filtered image. You can see that the contrast is significantly improved. I can see the thickness effects more predominant in this particular image. When I am looking at sort of weak phase object images or biological specimens, this kind of energy filtering can really help you get a very good contrast. So, this is the kind of information you can get from either the low loss spectra or from the images that are obtained by energy filtering around the zero loss or the low loss spectra. If I look at how the images are in this region, around the low loss region, this is what you have in an unfiltered case and this is what you have in a filtered case. So, when you have this energy filtering, you apply the slit, you can see that the spectra in this particular region are more kind of filtered, whereas here is an unfiltered case. So, you can distinguish the peaks specifically, and by applying filters around specific regions, you can get meaningful quantitative information from the EELS spectra. When I look at the low loss spectrum, you again get information from the zero loss peak and the plasmons peak, and from a ratio between the intensities of this in terms of the inelastic mean free path, I can specifically measure how much the thickness of my specimen is. So, this is another kind of information you get, and like I was mentioning in the previous lecture, it is always important to measure what information you get from a zero loss peak before I record core loss, and how the zero loss peak looks like after I record the core loss, so that if there is any drift in the spectrometer, I can actually compensate for the drift and the core loss information I record is actually accurate. If I look at the applications of the low loss spectra, I can use it for some kind of chemical fingerprinting with a very high resolution spectrometer, typically with a cold FEG or even with a monochromated system. I can actually look at this window of somewhere between 0 to 3 eV, and if I do it carefully, I can also look at the surface plasmon resonance effects, and I can look at the optical plasmons as well. And here I have the bulk plasmon information, and I can learn a lot about the functional properties of a material. I can also use this for chemical fingerprinting. For example, here I have the spectra from, I think, around 36 EV. I am not sure which element it corresponds to. This is typically carbon, I am guessing, or even aluminum L. Aluminum L, I think, is around 76. So, I am not sure, but you can get the chemical signature from here, and you can also determine the dielectric constant if I have some oxides. So, you can get all this kind of information from EELS. And looking more from the low loss spectra, the plasmons, which are longitudinal wave like oscillations, are corresponding to some specific energies which are weakly bound within the valence or the conduction band of the specimen, and these resonate and give you these plasmon peaks, and these are more dominant for light elements like lithium, sodium, magnesium or aluminum, and you get a characteristic plasmon scattering angle of less than 0.1 milliradians, and typical plasmon mean free path is around 100 nanometers. So, if your specimens are thinner than 100 nanometer, the plasmon peaks are not avoidable, you will inherently have them, but once you are below this inelastic mean free path corresponding to the plasmons, the height of these plasmon peaks, like you saw in this particular image here, would be very low. So, you cannot avoid them, but you will always have a signature, and from this you can measure the thickness of the specimen as well. So, the application of the plasmon peak is, for example, if I see a very thin specimen, I have a plasmon peak of this height, and if I have a thicker specimen, I have a plasmon peak like this. I can get the thickness information, and I can also get the chemical analysis, and I can also get the valence electron distribution. I can do band gap measurements depending on how much I have a shift here, and so on. So, it is a very powerful technique to get a lot of functional information from a specimen as well. So, I have just drawn a comparison here. The thickness of this particular specimen is 0.1 times the inelastic mean free path of the plasmon peak. If I assume that it is about 100 nanometers, this specimen is only about 10.3 nanometers thick, whereas this one, which has 1.172 times lambda, this is approximately 117 nanometers thick or 120 nanometers thick. If I carefully do this, I can measure the thickness also very accurately, and from other complementary convergent beam techniques, I can accurately determine the specimen thickness. And determining the specimen thickness becomes imperative for other quantitative electron microscopy studies as well. Now, if I look at how the high energy loss spectra are obtained, if I look at the band structure with all the intraband transitions that happen between the various energy shells, I have the emission of a characteristic ionization edge. The way I have the characteristic X-ray signal emitted and I have seen the EDS spectra generated, I also have ionization when a sufficient energy from the electron beam is transferred to one of the core shell electrons. The core shells are K, L, M, N shells, and once I have the transition from one of these shells happening, for example, when I have this transition happening here, I have the L23 transition. This is typically common for transition metals like copper, manganese or iron, and a corresponding peak is generated. The peak has a kind of a sawtooth or a triangular shape in an ideal scenario when you model it, but in reality this appears more like this, and you can actually measure based on the area under the curve what the valency is and where these peaks are and how many atoms are giving me this particular signature. So, this is reflected in the ionization edge in the EELS spectrum. The mean free path of these ionization cross sections is very large, and that is why you get a very low intensity. And when I see the dispersion, the zero loss peak is like this and all the plasmon peaks are like this, and then they die out. So, I have to go to specific dispersion windows and then I have to change the exposure times here and get a better signal. Good EELS analysis is mostly optimizing a good signal to noise ratio and doing a meaningful and a well thought experimental acquisition with specific energy windows. So, do you think these ionization edges are really sharp? I have actually told you that in an ideal case you see a triangular shape, but in reality they appear more spread out like this. This is the case with most spectroscopy studies as well, and the same physics applies here as well. And a little bit more on ionization edges, if I say that the critical ionization energy is EC, if the incoming electron beam strikes beyond this critical ionization energy and a specific quantum of these electrons are going beyond this threshold of this critical ionization energy, you start seeing the increased energy transfer and you get a near triangular shape which is observed as an ionization edge. So, if it is true, if it is an isolated atom scenario, but in reality when I have a group of atoms and I also have the other inelastic events like the bulk plasmons that are generated and you have the pleural scattering effects, you have a strong background effect, and once the background and the thickness of the specimen is removed, I would see the ionization edge giving you chemical information. So, the bonding effects, if you want to study, it is typically about 50 eV from the near ionization edge. If I want to look at the diffraction effects due to the atoms, which is similar to the information you get from XPS, I have to look at the extended energy loss fine structure. So, in EELS, you call this as EELNES, which is the energy loss near edge structure, and if it is this extended energy loss structure where you get the bonding information and the diffraction effects, it is within this particular energy window. If I want to look at the absorption effects similar to what you see in XPS, you have the extended absorption fine structure. You can also get this from EELS as well. So, if I look at how the energy loss spectra looks like from a typical data that is recorded, you have the core loss spectra here, and somewhere here, because of the background, my peaks are appearing somewhere in this region, but once I subtract the background, you can see that the peak which is having this kind of a shape appears a little more pronounced, and once you remove the background effects, you can see that this is perhaps the manganese L3 kind of an edge, and somewhere here you have the copper L23 edge, and somewhere here around 710 I have the iron L3 edge. So, for transition metals, again, because you have the partially filled or the fully filled d orbital, you get something called as the white line or the ionization edge, which appears like a single sharp line. So, depending on how the bonding or the valency is, if suppose copper is in a +2 or a +1 kind of a shape, +1 kind of a valency, I may see the white line appearance in the ionization edge. So, these are all signals of the valency and the spectrum related signatures, and you can look at the EELS database and get a lot more information on this, and there is plenty of literature available on this. And if I look at most finer details, the characteristic scattering angles for core loss energy electrons range from 0.2 to 10 milliradians. The scattering cutoff angles are between 25 to 200 milliradians. Typically, the entrance aperture is around 10 milliradian, you collect the entire spectrum. In diffraction mode, when I am at 800 camera length, these are tuned for some of our microscopes. Your 5 entrance aperture gives you a collection angle of 5 milliradians. So, with these numbers, with the software that you have for quantification, it can give you an idea on the quantitative information you get from EELS spectra. These are not accurate and ballpark figures. You have to do these measurements for your specific your specific instrument, and only then you can rely on them. Please don't use my lecture as a reference to give you. These are approximate numbers, and you can test them to get an idea of what kind of information you are recording. The most important acquisition parameters are energy resolution, the energy loss range and the spectrum dispersion, the dwell time if you are recording STEM EELS, or the exposure time if you are recording FTEM maps, and the total number of acquisitions you get and average. And there is something called as the jump ratio, which is the signal to background ratio. And for qualitative and quantitative analysis from EELS, for making a qualitative comparison, whatever is told you on the previous slide, it is not important to just get an idea of, has my specific element undergone a transition. Then you record a quick core loss spectra and you see how the shape of the peaks is, and that is good enough. But for a quantitative comparison, it is extremely important to maintain all the experimental variables constant, and only then after removing the thickness and the background effects carefully, you can start quantifying and get quantitative data. I'll give you an example from the Gatan imaging filter. You have the digital micrograph software. You can do the background subtraction, you can define the scatter angles, you can compare the changes in the peak, height, peak shift and so on. And also with other EELS models and open source scripts that are available to digital micrograph, you can get a lot of quantitative data. I'll show you an example from one of our earlier studies where we have done, based on different exposure times, how much oxygen or how much oxide is formed on an aluminum sample, and we've maintained most of the exposure and experimental conditions constant, and we were able to draw a comparison on with changing reaction times or exposure time, how the amount of oxide film thickness has changed and how much amount of aluminum oxide is formed. And if I compare the spectra with how the oxygen K edge, which is what we saw here, looks like in the image, you can see that for almost no exposure to an oxide environment, I do not see any oxygen cover. For an intermediate stage of 20-minute exposure, there is some measurable amount of bright oxygen signature here, and for longer exposure times to a reactive environment, I have a more uniform cover. So you can actually do sort of quantitative imaging with fixing these parameters and get how many atoms of oxygen or how many atoms of aluminum have combined with oxygen to form which kind of an oxide. And here qualitatively I can see how the thickness of oxide has changed over time. This is an example of how this EELS technique is powerful to give you information beyond what you can get from direct EDS analysis, which only gives you an information on whether or not an element is present. I have not gone into the details on copper. There is published literature on this, you can look it up. If I look at the fine structure and more fine in detail, what more information can you get from just, apart from just detecting the presence of a species, is how the ionized atom is bound, what is the coordination number of the atom, what are the density of states, how is the distribution of the other atoms around the ionized atom. This is termed as the radial distribution function. You can also do momentum resolved EELS. You can get the anisotropy of the chemical bonds. There is plenty of study happening now. This is kind of a hot topic. There are excellent published papers now over the last 5 to 10 years, I would say, where a lot on momentum resolved EELS is also being done. The fine structure details cannot be obtained from any other spectroscopic techniques. So once you know on which kind of specimens EELS can be done, from the fine structure, this is all that you can get. So if I look at the EELS near-edge spectra principles, when an atom is ionized from the ground to an excited state, I create a hole in the inner shell. For the electron to eject, it must receive enough energy, that is the critical energy that I told you. And beyond this, once the electron receives the enough energy and if it is able to escape into the unfilled state, this associates with an ionization edge, and when the electron that is ending up in each possible empty unfilled state is now filled in and there is an uneven distribution of empty energy levels, this is actually called as the density of states, and this is actually reflected in EELS near-edge spectra. If I look at the fine structure, upon ionization, if you look at the wave nature of the electron, if you have only a few electron volts of excess energy that can undergo a pleural or an elastic scattering from the neighboring atoms, that is when you get the near-edge structure, and this is a case of how near-edge structure looks like. But if you have some additional excess energy beyond a few hundreds of electron volts of inelastically scattered electrons, due to a stronger interaction. You can also get the electron energy loss spectra, which is the extended energy loss spectrum beyond the near Earth structure, and from this you can get plenty of information. I can show you an example from looking at the copper peak in a sample in which there is a change in the oxidation state of copper on reaction with a reactive environment. This is from a precipitate within an aluminum sample. In an unexposed or an unreacted state, copper appeared like a white line, but if I am looking at the near edge structure on reaction with oxide environment, you see the shape changes, and based on how the reaction is happening, this L3 and L2 peaks are also starting to appear. So, L2 and L3 peaks are very strong and sharp in an unexposed specimen, but on reacting with oxygen, because the binding is now changing, it becomes more and more broader. So, the L2 and the L3 peaks are appearing more broader here. So, this is commonly observed in transition metals, and here is from another example from some of my colleagues who did this study. This was way ago. Upon various exposures and formation of cobalt oxide, COO and CO3O4, by looking at how the near edge structure, fine structure is changing with different oxidation temperatures, the peak of cobalt oxide also changes, and this gives you an indication of the valency as well. So, from all these kind of examples and wherever EELS can be applied, in short, to summarize, I have given you several theoretical and experimental concepts related to energy loss spectroscopy. It is an extremely powerful spectroscopic technique combined with imaging from the nanometer or sub-nanometer resolution. Before one proceeds further, it is important to know the advantages, applications, the experimental challenges and limitations of the technique. Most importantly, EELS is extremely effective for lighter elements, for all the energy loss events that occur below 1000 eV. From the EELS fine structure, it is possible to get very important information on bonding, density of states that is not possible from other spectroscopic techniques. There is an exception of XPS, but the resolution of EELS is significantly better. When I talk about resolution, it is not just the energy resolution, but also the spatial resolution. So, one has to be aware on what sort of element systems EELS is most applicable to, and there are several limitations. I have not gone into all of this, but I hope I have been able to give you a broad flavor of what EELS is and what it can be applied for. So, with this, I will end our discussion on EELS, and moving further in the upcoming lectures, we will start learning about the aberrations in electron microscopy and how aberration correctors work, and show you examples of how or demonstrations of how aberration correction in TEM is done. And with that, I will end this lecture here. Thank you.